Hello everyone. So today we will be discussing a few problems on push down automata and how do we design push down automata. These are all deterministic push down automatas that we'll be designing. So by deterministic we mean that the language is well defined and for every input symbol we will deterministically transfer to the next state. So here it is 0 to the power n followed by a single 1, and the value of this n can be greater than or equal to 0. So let us first look at a few example strings here. So it is first example would be 1, wherein we say 0 to the power 0, which means 0 occurrences of 0. So the string will become 1. Next, let us take one occurrence of 0. So this will be 0, 1. The next possible string could be twice 0, then 1. Next would be thrice 0 plus 1, and so. So here 1 is the fixed variable that is coming, and 0 can be either uh, appearing 0 or more number of times. So let us see how to design such type of push down automata. So what is push down automata? As we have seen, it is nothing but a finite automata along with the stack operations included. So what we assume is that the stack contains an initial symbol, say Z0, and then we will be manipulating the stack and what happens to the transitions based on the particular input. So the input alphabet set here is 0 and 1. So the string, if you see, is formed of 0 and 1. And what we can place on the stack, that probably we can decide. So we say that for 0, we will use 0, and for 1, we can use 1. Okay, so now how to write the transitions representing the transition from one state to another. Apart from just the input, we also have to specify what happens on the stack. So if we consider the stack, we can perform push operation, we can perform pop operation, we can skip doing any operation. So for push, we will get probably some input, say A. For some input A, what we write here is what is present on the stack. So this is the stack top before doing any operation. Then we can put a slash or a arrow representation, and then what we write is this stack top, which will become stack top minus 1 because this is the push operation that we are talking about. And then if I have to push 1, I write 1 here. So what am I doing? If I get A in the input and the stack was originally containing Z0, what are we doing? We are pushing a 1 on the top. So what we list here is the top two contents of the stack. So this is the new stack top and stack top minus. So this is how the push operation needs to be written on the transiting arrow, say for example here. Next, let us talk about how to represent the pop operation. So for example, if the input is A and say there is 1 on the stack top. So what we have to do, we have to pop it. So we write epsilon here. So this is the pop notation, which means that whatever is there on the stack top will be popped or deleted. So this is the pop notation. How to write the skip notation? So for skip notation, say for example, I get A in the input. There is 1 on the stack top. I will let it be 1 as it is. So we are not doing any operation and the stack remains the same. So these are the three different operations that can be performed, and this is how they need to be written. So coming back to the problem, we need to have 0 any number of times. However, it can be 0. That is, it may not appear. So we can do a self loop here and we say if there is 0 coming up, if there is Z0 on the stack. So because initially the stack contains Z0, then what do? We will simply skip this ahead probably because we do not need to do any operation. We are not counting anything. So we are just skipping it. If we get zeros, we continuously loop in this. Further going ahead, if I get a 1, there would be Z0 on the stack. Again, I'm not doing anything, but I'm transiting to a new state, probably accepting this. So say this is Q1. So what happens if I get zeros? It will be going around in this loop for that many number of times. After that, if I get 1, it will go to the, it will go have a 1 in the input and accept the input as it is going to the final state. So this is a final state acceptance type of design. Okay, but if you see, we did not do any of these operations of push or pop. We have just done skip operation here because that was sufficient for this given problem. Now let us have a look at more problems wherein we will be using the other type of operations. So this second example here states that we need to have number of A equal to number of B. Now, how do we find this? Because it is A appearing n times followed by B appearing same n number of times. And what is the value of n? This should be greater than or equal to 1. So let us have a look at few example strings. So say if n is 1, that time I'll have one occurrence of A followed by one occurrence of B. If n is 2, I'll have 2A followed by 2Bs. If it is 3, we have 3As followed by 3Bs and so on. So let us think of a logic of how we can do this. Now, since this is a counting type of machine, I have to count the A's and correspondingly I need the equal number of B's. So here there will come up the uh, requirement of this stack. So what can I do? The first point that I can do is probably I can push some symbols, say 1, on the stack uh, when I get a in the input. Okay, so for all the A's that you get, so all the A's will be coming up initially. We will push 1 on the stack correspondingly. So say for example, I consider this as an example string. So we have 3 A's. So 3 times we will be pushing 1 here. So corresponding to these 3 A's, 1, 1, 1 will be pushed on the stack. Now, how do I ensure the A's are equal to B's? So as soon as you start getting B, you will start performing the pop operation. So for first B, this will be pop, next B and next B. So we'll have 3 pop operations because there were 3 push correspondingly 3 pop operations. So what we'll do is pop 1 from the stack as soon as we get B in the input. Now, how can we terminate? Now, if you see here, after 3 A's and 3 B's, there is nothing on the left in the string. So this can be represented as epsilon or you can represent it using a lambda expression. So what do we say if there in the string there is lambda and on the stack what will we have? The initial element that was there which is Z0. So if we have such a condition, then we will terminate. So if we say terminate, we probably go to the final state and accept it. So let us have this in the form of the diagram. So we have Q0. Now, if you see there is at least one A which is expected. So if I make a self loop here, in that case it will not be mandatory. So if it is one, you will have to go and transit the state to the next state. So when I get a, initially there will be nothing, that is Z0 on the stack. What are we doing? We are performing push operation by pushing 1, and there will be Z0 on the stack. So at least this one push of 1 will be there. Now after this it is not mandatory to have the other A's. But if it is, it can go in this loop. So again, if I get a, there would already be a 1 available on the stack. We again push a 1. So this can loop around for any number of A's. Now as soon as the A's are completed, you will start getting B. Now as soon as I get a B, what do we have to do? We have to start performing the pop operation. What will be there on the stack? 1. And we have to do the pop operation. So at least one B is mandatory. So this state change is there. After this, there may or may not be occurrence of B. But if B appears, there would be one because that many number of A's are pushed. Again, we'll pop them. And how do we terminate? Finally, in the string, if or in the input, I am receiving lambda or epsilon. On the stack, I have Z0. I let it be Z0 because I am in any way reaching to the final state. So since we are reaching to the final state, it will accept the string. So this is the design of PDA corresponding to the given language. Okay, now let us do one more example here. So if you see here, it says A should be appearing some m number of times. C should be there n number of times, and the B which is there in the middle of A and C, that should be sum of number of A's and C. So for example, again if you see here, it is m and n should be greater than equal to 1. So at least one occurrence is required. So the minimum string A, C. So now this is 1 plus 1. So we'll have two B's here. If I have two A and a single C, which is possible because M and N can be different. So then I'll have 2 plus 1, which is 3 number of B's in the center. If I have a single A, probably 3 C's, this is 3 plus 1, 4. So 4 B's at the center and so on. So if you look at the condition here, uh, we need to have A's followed by B followed by C in this given condition. Okay, now let us think of a logic that can handle this. So if you see here, as soon as the first A comes up, we can perform a push operation on the stack. So push 1 corresponding to the input A, and we keep on doing this for all the A's that are coming up. Next operation, we'll have B's. So corresponding to the A, we can pop that many number of B's. So what we'll do, we will pop 1 from the stack. But how much? So we'll pop 1 for the input B. Now, till when can I do that? Until the stack is empty. So if stack is empty, it means that number of A's that we had pushed is equal to number of B. Now if you look, what are we left with? Equal number of B and C. So again, after the stack becomes empty, we can start with push operation. So push 1 now if I get B in the input. So this I'll do until we get a C. And again, as soon as you start getting C, you will pop 1 for this input symbol C. So let us have a look at a small sample string. So say for example, we have two A's and two C here. So 2 plus 2 is 4 number of B's in the center. So what we'll do for the initial two A's, as we said, we will be doing a push operation. So for these two A, we will push 1 and 1 on the stack. Next, we'll do pop 1 and again pop 1. So now after this, the stack becomes empty. So what have we counted for these two A? 2 times pop operation is done. And what are we left with? We are left with 2 B's and 2 C's. So again, as the stack becomes empty, we will start doing the push operation for these 2 B. And again, when you get C, you will pop these 2 C. Again, you will have stack as empty. The input will have lambda, and that is how you will terminate. So let us represent this in the form of the DFA PDA diagram. So since it is at least one occurrence is there, we'll have to change the state. Otherwise, we could have looped at the first state itself. So as soon as Q0 gets a, it will transit the state. What will be there on the stack Z0, and what are we doing? We are pushing 1 on the stack. Now after this, I can have any number of A's coming up, but the stack will contain 1 and I'll push 1 again. Next, what will come up is this B. So as soon as I get a B, there would already be a 1 on the stack and we perform the pop operation. At least one B would be uh, popped off because there is at least one A coming up. So after this, how many number of B's we can get? Any number of B's. So until I have one on the stack, we keep on doing a pop operation. But as soon as we get B, but there is Z0 on the stack, that is the stack is empty. In that case, what we'll do, we'll just transit to the next state, say Q3. So now what happens here, as soon as I get B with a Z0, I will start doing a push operation again. So this is one Z0 here. And again, for any number of B's, I will be doing a push operation. Now, as soon as I get a C and there is one on the stack, I'll start performing the pop operation. And then there is at least one such pop operation going on. Apart from this, I can have any number of pop operations here. So what I'll do is I'll loop around. If I get a C and one on the stack, then I perform the pop operation. And at the end, if in the input I get lambda or if the string has exhausted, apart from this, there will be Z0 on the stack. Then what we do, let Z0 be as it is. And we go to the final state and this will be accepted. So this is the diagram corresponding to M plus N. Let's go to the next question. This is the same question as it was in the previous slide, but there is a slight change in the representation. So we have A, then it says we have number of B's. So this is some N, this is some M, but it says that M should be always greater. So how many C's should I have? C should be 3 minus 1 because this is 1 and this is 3. So this should be 2. So the logic would be same again. So if you see, for 1, I will perform push operation, correspondingly 1 pop for B, and I'll have the same number of B's and C remaining. So again you will perform push operation for the B's if the stack is empty and pop operation for the remaining C. So the logic will be same as the previous question. It is just the representation is changing here. Now, let us look at this one last example. Now, here it says we have n number of A's, m number of B's, but C should be m minus n. So, this is the same condition, but now it is saying that the number of n, that is number of A, should be greater than number of m, which is B. Okay, so for example, let us take a string of say 5 A's followed by 3B. So this is 5 minus 3, which should be 2C. So the logic which can be applied here is we can push 1 for the input A. So until we keep on getting A, we will be pushing 1. What happens? Correspondingly, we'll have 3 pops of B. So we will pop 1 for the input B. Now what is remaining? 2C. So if you see, these A's are equal to B plus C. Right? So again we'll perform the pop operation for the incoming input C. So if I have 5 A's, in the stack I'll push 5 times 1. Right? Then 3 B's, it will be 1, 2, 3 will be pop. Next comes 2C. Again we'll pop 2C. What will be there in the stack? Stack will have Z0 and the input is exhausted, so it will have lambda, or you can call it as epsilon. So then we will terminate. So let us just have this in the representation format. So Q0, we will transit to the next state. If I have A, the stack is empty, I'll push 1 on the stack. Then I can have any number of A's coming up, but there would be 1 already on the stack and we are pushing 1 again. So these two are the push operations corresponding to input A. Next, as soon as I get a B and stack has 1, I'll do the pop operation. So this is Q2. So at least one B is coming, so I'll change the state and then loop around here which says B getting 1. We'll do the pop operation. After this, you will start getting C. Again, 1 C is mandatory. So 1 is there on the stack. You will do the pop operation, go to Q3. Any number of C can come up. So to handle that, you will create a loop here. And after all these C's are exhausted, what do we get? We get lambda or epsilon in the string, that the string has terminated. There is Z0 on the stack. Let that be Z0. And we go to the final state and do the acceptance. So this is the PDA. So all these PDAs that we have discussed are deterministic PDAs because the language is fixed and there is a fixed condition, because it says there should be A, how many A's followed by how many B's, and then C. So thank you so much. See you in the next video.